Okay, hello everyone. We're gonna get started. I'm Thanush. You may know me from the camp website. So I am a 2024 US Physics team member, along with my other two co-instructors. I'm gonna be mainly teaching this week. So for the next couple weeks, we'll have Sorish and William also teaching. So the it'll depend. We'll see who's teaching each class, but most likely it will be Sorish teaching next week. He's in this call right now. William isn't here right now as well. Yeah, so we're gonna be using slides to explain everything, but basically everything that we go over and all of the stuff that we go over will be in the handouts for this week, which we will send out later, either today or tomorrow. So those handouts will basically have all the same stuff that we go over in the slides. So the same example problems and everything that I say out loud basically will for the most part, be inside the handouts in written form. But this is a perfect time to ask any questions if you're unsure about what's going on. Um, let's see. Yeah, so today we're going to be going over an intro to calculus, error, dimensional analysis, and differentials. Let's see. Yeah, the handouts will also have problems on them. So we encourage you all to work together on those. Ask us any questions if you have those. Um, And yeah, if you want to ask anyone else to join the server to join the class, feel free to do so. We want to get as many people help with physics as we can. And then as for USFO versus AP Physics, they're not entirely different, especially when you're first starting out. Physics is physics. A lot of the stuff that we cover today might not show up as much on AP Physics. Stuff like error analysis does not show up. And dimensional analysis doesn't show up explicitly, but you can use it to help you answer some questions. Yeah, we'll send out the handouts today or tomorrow. Okay. Anyone have any questions before we get started? Okay. All right, let's get started. So, calculus. So a lot of people might be wondering why we're doing calculus at all. So first of all, of course, the F equals MA exam doesn't require you to use calculus. None of the questions require calculus. And the same is, of course, true of AP Physics 1. Um, but the reason that we use calculus is because physics is fundamentally written in the language of calculus. Calculus is all about describing change, at least in the way we use it for physics. And that's extremely important for physics. Basically, every fundamental equation in physics is a differential equation. And we'll cover more what that means, but basically, we're describing how things change based on how things are currently. And that's just some differential equations. We're not going to be using those in this class, but yeah. So even if you think that you don't need it for F equals MA or AP Physics 1, we're not covering calculus very in depth in this class. It's not like you're going to be at an AP Calculus BC level after you're done with this class. This is more so just understanding the concepts of calculus and some basic operations so that you can use them in your physics problems, and especially so that we can use them to explain physics concepts to you. All right, so we're going to start with derivatives. So first of all, I'm just going to explain a little bit of notation. So there's lots of ways to write a derivative. So if we have this function s and it depends on x, this is how we can this is how we can notate a derivative with respect to x. And this prime here also denotes a derivative. In this case, it's with respect to t, since that's the variable in here. Same thing over here. And then this dot means that it's a derivative with respect to time. And then v is just a symbol for velocity. So I'll get more into how that works. But what you need to remember about derivatives is you need both the function and the variable that you're doing with respect to. So what is a derivative, first of all? A derivative describes how a function changes. So if we look at this function, here it's f, right? We can see that right now this function is increasing. It flattens out, starts decreasing, and then starts increasing again. So we can use a derivative to figure out how much exactly the function is changing. So when you get to calculus class, one of the first things you might see is this expression here. It's kind of long. It might not make much sense. But what it's basically saying is if you have this function here, what you can do is take a point, let's say at an x value x here, and then take another point that's a little bit to the right, so x at x plus h, and then you can draw a line between these 2 points. So the first thing you might think is, why do we want to do this? Well, drawing a line between these 2 points shows us how much the function changes from here to here. Wait, you guys can see my mouse pointer, right? Okay, cool. Yeah, so we can see how much the function changes from here to here. So obviously the function decreased, and we can also tell how much it decreased by subtracting f of x, these are backwards. So this is f of x here and f of x plus h here. So we can see that the function has decreased, and we can tell how much it decreased by. But of course, that's not good enough if we want to describe the change at a single point. Right now, we're describing the change between 2 points. So what we can do is take this h value and make it a little bit smaller. So now we would have a line that goes between these points. And as we keep making it smaller and smaller, we'll eventually just get how much the function is changing at exactly this point. And what we call that is the tangent line. So we'll find, let's say if we do the derivative here, we'll find the line that touches the function at exactly 1 point. And then by taking the slope of that line, how much it changes in the y direction versus the x direction, we can get the derivative. And so all this expression means is, if we want the derivative, and this is just two ways to write that notation, we'll take the f of x plus h is the second point, subtract it from the first point, and then divide by the difference in x. So just like how you would do a slope calculation, y2 minus y1 over x2 minus x1, it's the same thing here. So, sorry, let me start my annotation. Okay, so, yeah, so like I said, if you're taking a derivative here, you'd get a tangent line like that, and that gives you the slope here. So, oftentimes what happens with a limit like this is that if you plug in, if you just try to plug in h, well, obviously f of x minus f of x, or since h is 0, divided by 0 is obviously 0 over 0. So that's what we call, oh, can you all see the annotation? Okay. I'm writing at the top of the screen. Okay, 1 second. Can you all see this? That's weird. Okay, I will join from, I can see yours. You saw it for a second. That's weird. Okay. Yeah, we can indeed, I can see everyone else's annotation. All right, yeah. Sorry, just start talking. What did I do wrong?
Uh, use like the annotate tool on Zoom, I think.
That is indeed what I'm doing.
Can you guys see my annotations?
Yes. Or can everyone else see this? I'm not annotating in white. No one can see the annotations.
Oh, it disappears after a while. It's weird.
Okay. We're gonna fix this for next week. For now, I'm gonna join on my phone and broadcast my notes up. Okay. Sorry about that, everyone. Yeah, I don't know why this is happening, but
Recording in progress.
we'll send out the handouts either today or tomorrow. Okay. So yeah, for some reason I can see everyone's annotations, but I'd appreciate if you all did not annotate on this screen. Okay. Let me share. Okay, this is annoying. One sec. Can you all see now? Still no. Okay. Um, I will. I'll just open a separate whiteboard and use that for now. We'll fix this by next time. Okay. Well, at least you all can see the whiteboard, right? Okay, cool. I'll just use this to explain what's going on in general. But for here, yeah, so a derivative just tells us how much the function is changing at a single point. And the reason the derivative is a function is because usually when we take a derivative, we list out, so f prime of x just gives us the derivative at every single point x. So we could find the derivative at this point here. Let's say it's just like x equals 5. And then that would be f prime of 5, would be the slope of the tangent line right here. And so the derivative is a function because it returns the slope at every single point. Okay, sorry about that. Anyone have any questions about what derivatives mean conceptually? We're gonna go over how to find a derivative, but sorry. Okay, no questions. Okay, so um, one other thing I wanted to mention about derivatives is the reason we use s here. S, you can also use d, but you can see why we don't want to use d. We're using s to represent some sort of distance function. So how much distance a particle travels as a function of time. And so if you take the derivative of this distance, you'll get a commonly used function in real life, and that is your speed, because your speed is just how fast your distance is changing throughout time. And so if you're going at a constant speed, you can just say, oh, I'm going at 60 miles per hour. But if you're speeding up, then maybe you want to say that after 1 second, I'm going at 10 miles per hour. After 2 seconds, I'm going at 30 miles per hour. After 3 seconds, I'm going at 40 miles per hour. And therefore, you would need a function to describe your speed. And your speed is just how much your distance is changing throughout time. And if you're constantly speeding up, your speed is never going to be the same. But we can still find, um, if you're constantly speeding up, your speed is never going to be the same. But we can find at every single point how fast you're going at that exact time. So even if your speedometer needle is moving upwards constantly, if you take a photo of it at any single time, you'll find that it's pointing to some number. And that's what we use the derivative for, to figure out what we call the instantaneous rate of change. And then, of course, if we take a second derivative, which just means taking the derivative twice, we can find the acceleration because that's how fast your speed is changing, and so on. Any questions about that? Okay. So I was going to write this on the slides, but we're going to do this here. Um so some just like we have notations for our first derivative, like say f prime of x, we can also use we can also write our second derivative by saying just putting two prime symbols there. And just like we can take s dot to mean the first time derivative, well, it's really simple. You put two dots to get your second derivative. This one might seem a little weirder, but you're basically using the ddx twice, and you treat the dx as one piece, which we'll cover later. So therefore, the second derivative, oh, this is in the wrong column. Anyway, um, the second derivative, when we use just ddx here, is written like this. So we use a d squared and a dx squared. And that's the same if we put even if we put this s up here. And then one final thing is that we can continue this for however many derivatives we want. So if we take the derivative of this function, we'll get a third derivative and so on. And that just means putting more primes, putting more dots, and increasing this power to 3 or 4. But one other thing you can do is change this double prime to a parentheses with, say, if you want the fifth derivative, you put the 5 up here. That's just notation. This will all be in the handout. But just so that if I use any of these any time in the course, you can tell what it means. Just remember dots always mean time derivatives. Okay. Yes. So yeah, okay. The reason it's not ds squared is because what we're really doing is putting this here, and then we're putting another ddx out here. So if this is your first derivative, you're literally just taking another derivative of your first derivative. And so the way we do that shorthand is just squaring the d's. And some people think, why isn't this d squared as well? It's because we treat this as one object. You can literally think of the dx as a variable of its own. So it's just a two-letter way to label one thing. Yeah, so what McKenna said is right. Well, ddx isn't really a function. The correct term would be operator, but yeah, it's basically because we're acting on this s with the ddx. So the s is just out on its own, and this is like what we're doing to it. Just like if you take f of x, right? If you're putting a function inside another function, you're not gonna. It's not like we're squaring this. You know what I mean? Um, yeah. And actually, the notation for this is f squared of x without the parentheses, which is why the parentheses are important. Okay, so coming back to here, Derivatives are important in physics because lots of things are derivative. Let's think about F equals ma, for example. Well, that is really a differential equation. And we'll cover what differential equations means, but the acceleration, like I already mentioned, is the second derivative of position. Basically, the first derivative of position tells you how fast you're going, how fast your distance is changing. And then your second derivative tells us how fast that's changing. So already there, we see that one of the simplest equations in physics is based on derivatives fundamentally. And we don't have to think about it that way, right? Because we think, oh, I know what acceleration is. It's just how fast I'm speeding up. But when your acceleration isn't constant, when it's changing constantly, then it makes much more sense to use these tools from calculus. And a lot of time in calculus class, you'll spend a lot of time working with this definition of a limit to find your derivative. You'll do a lot of stuff with limits to just make sure that you really fundamentally understand it. That's not really necessary in physics because when we work with functions, we'll usually work with nice functions, which just means taking derivatives is easy. And we don't really have to worry about the mathematical intricacies of everything. Okay. Great. So, derivative rules, this is going to be in the handout, and you're going to have to, if you're new to calculus, you're going to be referencing this constantly, and that's okay. The way that you get good at calculus is just by doing a bunch of problems, and we've included a bunch of problems in the handout. So, you can prove all of these by using the limit definition that we showed earlier. Um, yeah, so but if you're going to be fluent at calculus, and which means being fluent at physics, you're going to have to basically know these. And the best way to know it is by doing enough problems with it. So we're going to do an example. And if you haven't seen any of these laws before, you're probably going to think it's going very quickly. And that's okay. Just come back to the recording, come back to the handout and work through it slowly. So let me just see if I have any comments here. Yeah, notably, e to the x derivative is e to the x. That's why e is a special number. One of the many reasons why we consider e a special number. And another thing about power laws, this is x to the power of n. N does not have to be an integer. So notably, if we switch to this tab, sorry, sec. Okay. Um, Notably, the square root of x is equal to x to the power of 1/2. So we can use the power rule on it. So if you're ever confused how to take the derivative of this is um, with the power rule, we know that x to the n goes to nx to the n minus 1. So we see here that since the power is 1/2, we just bring the 1/2 down, and we take x to the power of 1/2 minus 1, which is negative 1/2. Which, since I've done calculus for so long, I would just go directly to this form. Since I've seen that problem in my homework sets so many times that I know that the derivative of square root of x is 1 over 2 root x. And if you're new, just working through this kind of stuff a lot will make you better. So just another example, x to the minus 1, that's negative 1 over x squared. And I'll just give you all a minute to think about that. And then if anyone still doesn't understand, I will go over it. And please don't hesitate to ask if you don't understand. The power rule does work when n equals 9. Wait, what? Yeah, it works for the derivative. The power rule always works for the derivative. Yeah, if you're new to like ignore this, but the reason that it doesn't work for negative 1 for integration is because you would get division by 0. Um, Notably, if you're trying to take the derivative of a constant, you can literally write that as x to the power of 0 and take the derivative with power rule, and you would get 0. So it still works out. Okay. Anyone still want me to go over? Or I guess I'll just go over it. Um, don't if you don't feel like asking. Well, we know. I guess I should have written in this way, but that's what that is. X to the power of -1. So we'll bring down the -1 and decrease the power of in the numerator by 1, right? Which makes x to the power of -2, which is how we get to this point. -1 over x squared. So now I'm going to do a slightly bigger problem. So again, if you haven't seen any of these rules before, just um yeah, I was planning to do it on this page, but I think if you don't know, if you haven't seen any of these before, probably take a screenshot of this just so you can look to the side while I go over the next problem. Give you all a second to do that. Okay, I'm gonna switch back and forth between tabs. So um sorry, I was intending to do this on the slide itself, but we're gonna do it over here. So again, if you didn't catch all the rules, I'm going to explain them, so don't worry. So we're taking the second derivative. Now, there's nothing special about taking the second derivative. We know that the second derivative is just the derivative of the first derivative. So the first step is we have to find the first derivative. There's no way we can get to the second derivative without getting the first derivative. So we have s, we want to find, oh yeah, notably, wait, I'll just rewrite it here. Um, I wrote this, I wrote this way, just because it's easy, but x just means e to the power. So this is the same function. Um, and the way order of operations works is you're doing this first. So yeah, you do the x squared first. Yeah, and if you do physics long enough, you're gonna solve a differential equation that has a really ugly thing inside of this. Use the x function. Don't put it all up here. Anyway, small side note. But yeah, the first thing we notice is this looks weird. To find the first derivative, well, what we can do first is check and see if we have any laws that can handle it. E to the power of x squared. Well, I see an e to the x here. I know that x to the n, if we put n equals 2, that gives us x squared. But like we don't have any e to the x squared. So let's look over here. This is all our laws for trying to put two functions together. So multiplication by a constant, we don't have a constant in front. Sum of functions. Well, we're not adding any functions together. Product rule, we are not multiplying anything together. And then notably, we're not doing a quotient. But we see here that the chain rule is for f of g of x. That's one function inside another. So coming back here, can we write this as f of g of x for two functions f of x and g of x? Well, it certainly looks that way. All we'd have to do is let f of x equal e to the x. And then let g of x equal x squared. Now, does everyone understand why this works? Why we can write, now we have s of x equals, that's weird. Okay. Why s of x equals f of x, f of g of x, sorry. So we're plugging g of x into f of x. Yeah, so x stands for exponential. I rewrote the function here. So this and that mean the exact same thing. Um, yeah, so the reason we can do this is if we take g of x, that's x squared, and then stick it in here, we're putting e to the power of, replacing this with whatever we put in, e to the power of x squared. Does everyone understand that, or do you want me to like try to explain it a different way? Okay. Yeah, if you don't understand, don't feel free to just ask. Okay, so now I'll just copy over the rule as prime of x. We have this. So s prime of x is equal to f prime of g of x. Sorry, I should show this. Times g prime of x. And that's just the chain rule. Why'd we use the chain rule? Because we have a function inside another. So let's do these parts. We need to find f prime of x. All right, well, let's go back to the sheet. E to the x derivative is just e to the x. That sounds good. And g of x equals x squared. Well, that looks like a power law. We bring the n down and decrease by 1, we just get 2x. So g prime of x equals 2x. Does everyone understand those two? I know I went kind of fast on g of x, but this is a very, very common derivative. Okay. Yeah. Now we'll plug everything in. F prime of g of x just means putting x squared into this. So we get e to the x squared. And we need to multiply by g of x, which is g prime of x, sorry, which is 2x. So I'm going to put that in front. And that's our first derivative. In the interest of time, I may not do the second derivative. Yeah, I'm going to skip the second derivative. But how do we do it? Well, or maybe I will do it fast. Just the prime is a symbol for derivative. F prime means the derivative of f with respect to x. So just like s prime here means we're taking the derivative of s with respect to x. So that's like if you plotted s as a function like that, then s prime would be like the slope here, for example. And the same is true for f prime, g prime. That's just the derivatives of those functions. So what we're saying here is if we want like, say the slope of s at 2, we would need to get the slope of f and find out what the slope is of f when we plug in 2 to g of x. So let's say g of 2 is, well, we know what g of 2 is. G of 2 is 4. So we need to find the slope of f at 4, because g of 2 is 2 squared, which is 4. And then multiply by the slope of g at x equals 2. Okay. And then finally for some more of intuition about how derivatives work, just so that you guys can understand. So this is the graph of x squared and its derivative 2x. And so we see that here the derivative is negative, and we see here that the function is decreasing. Well, that makes sense because the slope is negative, so the derivative has to be negative here. We see that the function flattens out here, so that the slope of the tangent line is 0. And then we also see that the derivative is 0. And then again, the slope slowly increases and the function increases this way as well. And then we can do the same for any of these functions, right? So if we look here at e to the x, well, I'm just going to plot it because its derivative is itself. We see that as we get farther and farther to the left, the function flattens out and it also goes to 0. Well, that makes sense because as it flattens out, the slope slowly goes to 0, the slope of a flat line. And then the same thing goes as we get up here, right? Like right here, when the value of the function is 1, we know that the slope of this line right here is 1. And I can show that to you by plotting the tangent line, which is just y equals x plus 1. So we see here, no matter how much I zoom in, these two never intersect. Because, well, they intersect at exactly 1 point. So this line barely touches the exponential function, and it has a slope of 1. And that's what the derivative here shows us. Since the derivative of e to the x is e to the x, we get a value of 1. And so we can literally do the same thing for, let's say, well, e to the x squared, right? It looks like that. Well, we know that we just found its derivative. That's 2x e to the x squared. So right here, as it flattens out, it gets to 0. While as a negative derivative, it has a negative derivative here. And as it starts increasing, the derivative starts increasing too. So again, it all makes sense. Okay, so that's just a little bit of intuition about derivatives. I just wanted to go over that just in case you didn't understand. When we come back to all the mechanics of it, it's kind of hard to, sometimes you get caught up in all of this stuff and you kind of forget what a derivative really means. And that's what it means. So anybody have any questions about that, about the graph stuff? I'll show any graphs if you want me to again. Okay, so we found f prime of x here. So f prime of g of x is, well, we know g of x, right? G of x is x squared. That's right here. So f prime of g of x just means f prime of x squared. The prime doesn't make it any special. It's just like a name for the function, right? Like you guys have done function evaluation before. And so it's literally the same thing. This is just a different function. Like if you really wanted, you could call this like c of x, right? Or d of x for derivative, and just it would be the same. And that just means putting x squared into this here. And so the function input we chose here was x, which means whatever this is, whatever shows up here, we have to replace it here. So since we have an x squared here, we replace it with x squared up here. That's how you do that. And then you multiply by g prime. So that's how we get to this point. Okay, and I'm not doing the second derivative, but what you would do is just use the product rule because you have a product of this function and this function. This is x to the power of 1, or you can use the linear rule that we have on the slide. And then you take the derivative of this and multiply by this. So that's essentially right here. This example is on the handout, so including the second derivative. So you can look at that later if you want. Let's see. Yeah, and then the answer is right here for the second derivative. Okay. And now I have some more stuff to explain about derivatives. So let's go back to Desmos. Okay. So one more important thing that we can use derivatives for is to find maxima and minima. So just where a function is greater than everything around it and where a function is less than everything around it. So, what you could do is, I actually don't know how you do. You can't do this without algebra. So what you notice is the function is increasing until it gets to the maximum, right? So what would increasing mean? Well, increasing in a calculus standpoint means that it has a positive slope because any line tangent to it is pointing upwards. Then we get here, and boom, it levels out. So if you draw a tangent line here, it has to be flat, right? So let me draw that tangent line real quick. Oh wait, yeah, it's just x equals 7. Okay, or y equals 7, yeah. I did the entire derivative. Okay, but yeah, so we see that it flattens out. And we also see that the slope of this line is 0. And so, and then it gets negative afterwards and it comes back down. And we can say the same thing down here. So now with calculus, we have a really, really good, easy way to find maxima and minima. It's just find where the function has a slope of 0, and boom, that's your x value where you have a maxima or minima. Oh, oops. Someone asked why we have an extra g prime of x. Well, um, one of the exercises on the handout is to derive the chain rule. And if you really want to figure that out, like you can derive the chain rule. Um, but the easy answer and the answer that's relevant for physics is because the chain rule tells us that that is correct. We have to multiply by g prime of x. Intuitively, though, what you can think about is if you have this function f of g of x changes by a certain amount, which changes g by a certain amount. That shows up here. And then because x changes g, that changes f by a certain amount, which changes s. So this shows how much x changing changes g, and this shows how much f changes at a certain value of the input. Yeah, please ask questions out loud because if I'm on the slides or the whiteboard, I can't see your questions. Okay, yeah, that answers your question. That's good. What does the second derivative tell us? So for example, if you want to say the first derivative tells you the instantaneous velocity, the second derivative tells you the instantaneous acceleration. So let's say you're going on highway, you're slowly increasing by like 5 miles per hour every minute, your velocity, right? But then boom, you decide you see someone brake really hard in front of you, you slam on your brakes, and now you're decreasing your velocity by like 20 miles per hour every second. So if you take your second derivative, what that would show up like is the graph of your second derivative would sorry, imagine that's straight. Anyway, so your graph of your second derivative is like this because this is the amount you're, or it's probably better to, okay. So your your acceleration is like, okay, your acceleration is slightly positive, so you're speeding up a little bit by let's say 5 miles per hour every second. Okay. But then boom, you slam on the brakes. Now how fast you're changing, how fast your speed is changing is very, very negative. You're slowing down really quickly, right? And so let's say that's like 20, negative 20, right? And so is what the graph of your second derivative would look like. If instead you wanted to plot your first derivative, maybe you start at some initial velocity, it's slowly increasing, but then boom, it starts decreasing, right? So the derivative of this function, first it's slowly increasing, that's this value, and then it's sharply decreasing, that's this value. Does that make sense? Yeah, this line, when you stop the car should stop. So um that shouldn't go down here, but I know sour, I know. Yeah, so like you stop, the car stops here, right? So ignore all this stuff. But yeah. Does that make sense? Uh okay, so let me redraw this. Or let me just I could do it on decimals, but I'll just try it. Um, so I'll start like this, okay? So first of all, let's say that our position looks like this, okay? Um, Actually, I don't know if I want to draw this position, but if like our velocity is slowly increasing and then slowly and then sharply decreasing, right? Sorry, wait. Kerem, how do you? I don't know how you say your name, but can you explain your question more? Yeah, like if you press your brakes really hard, your speed is gonna approach zero, but your acceleration is like -20, right? Because like let's say you're slowing down, that means your speed is decreasing every second. And decreasing every second just means like you're adding a negative number to your speed, right? So every second your speed gets smaller and smaller because you have a negative acceleration. Does that make sense? Oh, sorry. Yeah, I tried. Yeah, I put both of them on the same graph. Um, and then Victor, does that make sense? The explanation of what the second derivative tells us? Yeah, okay. Sounds good. All right. Yeah, so this is back to our discussion of minima and maxima. Like I said, it's pretty easy to see on the graph that if the function is at a maximum, well, it gets flat. And that's because on one side you're getting bigger and one side you're getting smaller. So to get to a maximum, you have to have a flat value for your function. Sorry. So we just have to find where the function gets flat or where its derivative is zero. So if I plot the derivative here, we see that right here, yikes. Thank you. Okay. Um, yeah, we see that it goes to zero when this stops, and it goes to zero when this is flat as well. So if we find these 2 points by setting our derivative equal to zero, then we can get these two points here, our minima and maxima. Does that make sense? Okay. If it doesn't make sense, I'm gonna do an example, and if you still have questions, please ask. Okay. Okay. So this is our example. Where's the pen? Oh, okay. Here it is. Okay, so sorry. So we got to find this maximums. So let's just graph it first. What does the function even look like? Well, it looks like this. And my first thought is that makes sense because this x term, well, when x gets really small, like very negative, this becomes very negative as well. And when when x gets very large, e to the negative x gets very small. So this has to go down again to zero. So just thinking about this, I know that when x is very, very negative, that the function has to be very, very negative. And when x is very, very large, the function has to go to zero. So somewhere in between, I think it should get to a maximum. So that's how I know there's a maximum. If you take a calculus class, you'll learn all about using the second derivative test and stuff like that to figure out if you have a maximum or minimum. But in physics, what we can usually do is either look at the function and use a little bit of limiting cases arguments, which we'll go over later, to basically say when x is very, very small, we think that the function will act like this. And when x is very, very large, the function will act like this. So somewhere in between, it has to have a maximum. Or you could also argue, like one of the questions on the handout will show, like if you have a physics problem, often you have context in the physics, right? You know that if you're going to throw a ball, there's some angle that you're going to get a maximum distance at. It's not going to be a minimum because if you throw the ball straight up or all the way flat, you're not going to get your maximum distance before it hits the ground. So either from one of those two places, you can figure out if you're going to get a maximum or a minimum. So now let's actually do the derivative. So I'm gonna go through this a little quickly. We're gonna run out of time otherwise. But using the product rule, we'll take the derivative of the first part and leave the second part alone. Derivative of x is just 1. And take the derivative of the second part, leave the x alone. Um, so how did we get this? The derivative of e to the negative x, well, that's like chain rule. That's like e to the x, sorry, but with a negative x plugged in here. So derivative of e to the x is just e to the x, but with the negative x plugged in. And then the derivative of this is -1, so that goes out here. That was extremely fast, and I think if you haven't seen calculus before, you're not going to understand that, but just go through very slowly, take the product rule, and when you get to this term, use the chain rule, and you will see how it works. And the same thing is in the handout, explained fully, so that should be good. Anyone have any questions so far? U sub is not U sub is for integration, notably. We haven't gotten to integrals yet. Um, this is a derivative. Um, yeah, I'll discuss what U sub is, but um, yeah, basically it's chain rule. So it's this rule right here, which we spent a lot of time doing, f of g of x, right? It's this rule, but our inside function g of x is really, really simple. It's just negative x. So um, you basically you to find the derivative of this term, you take the derivative of e to the x, which is e to the power of whatever, and then you multiply by the derivative of this, which is -1. Yeah. And then solving this quickly gives the x equals 1. Um, you can work through it, or you can just plug it in and see that that leaves e to the negative x minus e to the negative x, which gives 0. And the reason, again, we're setting to 0 is because when the derivative is 0, the function is flat, right? We see that the tangent line is flat, and that tells us where our maximum is. And how did I get this 1 over e value? Well, we know that x equals 1, and all we have to do is just plug back in. So 1 times e to the -1 is 1 over e. Sorry, I know that's quick, but we notably have an hour left and quite a bit of stuff to cover today. Does that make sense? If you don't want to ask now, you can notably also ask in the server afterwards. But yeah, if please ask if you have questions. Okay, sounds like no questions. Um, we're gonna do this a lot using derivatives to find maxima and minima, so you will get practice with it. Okay, we did all of this. Now we're on integration. So integration is the opposite of differentiation. So you've taken a derivative, you can undo it with an integral. So I haven't written this on the slide, but so if we take this part here, the integral from a to b, what it gives us, if this is f of x here, is this area under this curve. So if this is our a value of 1 and b value is 3, then taking this integral with a and b written here just gives us this area. And that's the dx just tells us what the variable that we're integrating is, right? Just like we had a d dx in our derivative, it's the same thing here. And the reason the symbol is this is it's actually an S, but just really long. So if you imagine drawing an S and then just making it really long, that's an S. And the S stands for sum. Because what you can think about is this is like taking a bunch of little rectangles under this curve and adding them all up to get their area. So an integral just gives you the total amount that a function has if you add them all up. So what's a good example? Well, like I said, it's the opposite of differentiation. So let's say you're moving at a certain speed, and this is how your speed is changing through time, right? So if you start at this time 3, and you take your integral of your speed all the way to sorry, your time 1 and get all the way to time 3, what you'll actually do is you'll figure out, so in this tiny amount here, I moved forward by this area. So I started with velocity of 5, and for a split second, I moved forward, and I got through like, let's say for like a millisecond, I moved forward with speed of 5 meters per second. I moved forward like 0.0005 meters. And then for the next split second, I moved a little amount, and the next split second, and so on, until we figure out how much total distance I've moved by adding up all the pieces of our velocity. Does that make sense, everyone? It's just a way to add together a function that's constantly changing. Just like a derivative was figure out how much the change was for a function that's constantly changing. Right now, instead of we can use this integral tool to get this the total sum of the area underneath. So what's actually interesting about integrals is we have two types of integrals. We have what's called an indefinite integral, which is right here. That's also called an antiderivative, and a definite integral. So let me just write that down, or I can't annotate. Sorry. Yeah, the annotation was working until we got this many people in a room. So yeah. Yeah, so this is the indefinite and definite. So it's just whether there's bounds. Bounds is just the A and B values that we put on the left and right. And what the indefinite integral does. So I already explained what the definite integral does, right? So it gives you the area as you go from A to B. But what the indefinite integral does is it gives you a function. We'll call it capital F of X, right? And that function tells you how to figure out what this definite integral is when you change your bounds. So if your bound is A to B, you have to just do capital F of B minus capital F of A. Okay, does that make sense, everyone? Okay, no questions. I will move on, but if you have questions, feel free to ask. So you'll see in calculus class, oftentimes teachers will put a plus C. Don't forget the plus C, stuff like that. The reason we have a plus C is just because if you do f of b minus f of a, if you add like 5 to both of these functions, it'll cancel out. So it doesn't matter what the extra constant in front of the equation is, because it'll cancel out eventually for anything that actually matters. And the actually mattering part is this definite integral. So now I didn't tell you guys how to find a um, integral, but it's really easy. And I say easy because, or I'll say it's really simple because um, taking integrals is a lot harder than taking derivatives. Because as I've just written out, you're basically finding a function that if you take the derivative of, you get your original function. So we already took the derivative of x squared, right? And we got that it was 2x. Well, that means that if we put 2x in here, we'll get x squared back out here. So it's literally the opposite machine of a derivative. And that's what this means here. If you take the answer of your integral, take the derivative, you get your original answer back. McKenna, I'll go over that. Okay, does that make sense, everyone? So, a lot of you will encounter integrals that are hard. And they're hard because imagine you just took imagine you saw that nasty second derivative from before, right? Right here. And someone just gave you this and told you, yeah, figure out what the original function is. That might be kind of hard because this is really ugly. Even though this original thing is very simple. And for derivatives, you have a set list of steps to go through. You have a few rules and you know which rule to use in which step. That's not always true here. And so a lot of calculus class is mostly figuring out, like learning a bunch of integral techniques that can help you solve hard integrals like this. In physics, we mostly won't be doing that. Yeah, and there's also a lot of algebraic manipulation as well. Um, That can be true of derivatives sometimes, but mostly, yeah, with integrals, like you can have like really nasty expressions, and sometimes you actually can't even figure out the you can't write uh an antiderivative or an indefinite integral in terms of the functions you know, like sines, cosines, exponentials. Like a lot of the time, like let's take a function as simple as e to the x squared. We don't know what this is, or actually, it's not that we don't know, it's that we can't write it in terms of like sines, cosines, natural logs, exponentials, polynomials. So what are the best we can do is define um a new function for it, and that's about it. And that's just in this case it's called the error function. But um like a lot of times there's literally no solution. So what we can do is also like use a computer and just add up all these rectangles, like just cut this area into very, very thin rectangles and add them up with a computer, stuff like that to get our integral, our definite integral. So, integration is harder if you're given a harder function, but if you're given something like 2x, well, you just got to do the derivative backwards. Um, and so the common integral you will see is of x to the n, power n. Um, and that goes to x to the n plus 1 over n plus 1. And this is just because if you take the derivative of this, well, the n plus 1 comes down, cancels with this here, and then this gets decreased by 1 back to x to the n. This doesn't work for n equals -1. Yeah, it doesn't work for n equals -1, but we n equals -1 case is the 1 over x case, right? And well, we know that the derivative of natural log is 1 over x. So if you take the integral of this, right, dx, sorry, d, that gives us ln of x. So this is the one time you can't use the power rule. You have to use this. I'm sorry, you can't use the power rule. You have to use this. Yeah. And other than that, you might see something like an integral of e to the 2x, and someone in the comments is going to say u substitution, and that is entirely correct. But for the purposes of right now, we can just say, well, based on the power, not the power rule, based on the chain rule, I know that when I take a derivative of e to the x, this 2 will come down. So how about I just say the answer is 1/2 e to the 2x. Why? Because if I take the derivative of this, the 2, you get e to the power of 2x multiplied the derivative of the inside. The chain rule tells us we have to multiply by the derivative of this. So the derivative of this 2x is just 2. Multiplying 2 by 1/2 just returns this, since we already have this part. Again, if you're not used to doing chain rule yet, that's going to seem, like you don't know where it comes from, but um just taking integrals oftentimes is being really familiar with the end results of what a derivative would get you, and then kind of doing it backwards. You can either do it with guess and check, or in calculus classes, you'll learn a lot of methods. You'll learn trig sub, u sub, integration by parts, partial fractions, all this stuff. My advice is if you're doing calculus just for physics and you're getting started, know the power rule, know this. This will show up in a lot of differential equations. And other than that, or also know e to the power of x, right? Um, and then remember how the reverse chain rule works for a simple linear thing like this. And then if you don't know how to do an integral, put it into Wolfram alpha, right? Like go to Wolfram alpha here. Let's say like, oh, I don't know how to do the integral of 2x over x to the power of 4 plus 1, right? And then you go down here and Wolfram alpha is just like, oh, great, this is the answer. So you click the step-by-step solution, and it's not going to tell you everything, but usually here it's going to tell you enough that you can figure out what's going on. So what I have to do is do a substitution. All right, so let's say it tells you do integration by parts. Maybe that's when you decide to learn integration by parts. But integrals in general are lots of experience. It's very useful to know what kind of method to use. If you're still not familiar with the derivative, this is very important. It's how much an function accumulates over time. You can figure out how to actually do the integrals later. For any derivations we have, it's probably like next week we're gonna do kinematics. You're gonna see the integral of t dt, right? That's just t squared over 2. Like you're not gonna see anything too complicated for now. Okay, differential equations. So a differential equation just tells us that it's just a function, it's just an equation with a function. So x is a function of t here, and its derivative. So this is the first derivative of x. So I'm going to rewrite that differential equation, and I'm going to rewrite it a few different ways. Um, so notably here we have x as a function of t. So this might be like where your x coordinate is as a function of time if you're walking, right? Oh wait, sorry. I don't think I asked if anyone has any questions about taking integrals. No? Okay. If you have a question about something and I've oh yeah, I haven't explained that yet. Or I think I did, but I'm in the process of explaining it. But um if you have any questions about something that I've moved on from, don't hesitate to ask. I will go back. Okay. A differential equation is just it's an equation, equal sign. There's a function, that's x here. And there's also the derivatives of that function. That's this. So it's just an equation that has a function and its derivatives. And what this differential equation here says is the amount that x changes through time, which is commonly called velocity, right? So my velocity depends on my x coordinate. So let's say my house is the origin. This says the farther I go from my house, the faster I'm going to run away from my house. Okay, that's basically what this is saying. But what we can do is if we want to ask, how does x change with time? Like if I'm running faster from my house, the farther I get away, how many seconds will it take me to get to this tree 20 yards from my house? Well, what we have to do then is solve this differential equation. So, Victor, does that answer your question? Okay. And the k is just a number. Like it could be 5. We just use k. You'll often see like a physics equation with a bunch of constants. Um, and you might not be used to that, right? Like in a lot of math classes, you might see a complicated function, but there will be one variable. And you come to physics and you have this huge expression with a bunch of variables. Most of them will be constants. And that's just because, if we start plugging in 17.046 into our equation and like 3.89 and 9.81 and all these numbers, then it's going to look really ugly real fast. And it's really, really much easier to keep track of these variables than it is to keep track of like 7 point decimals. And so K, it's a constant. If it confuses you, replace it with 5 and do the entire problem. It'll look exactly the same. And there's more benefits to doing this. In general, I'd say if you're solving a physics problem, try to make everything a variable if you can, because or like use a letter instead of a number. Because let's say you solve your physics problem, and then your teacher like you're chilling, you're in class, 30 minutes on Brawl Stars, and then your teacher comes up and says, "Oh yeah, by the way, there's been a mistake in question 7. This is actually supposed to be 3.74." And now you look down at your paper and you've written down one number and you have zero clue. You're like, oh God, I got to resolve this entire question. Instead, if you write down the answer in terms of variables, boom, you plug it in, you're done. Right? You plug back in and you're done. Okay. So let's solve this, right? First, I'm gonna use all our derivative notations to write this, just so that we can get practice with that. So we can call this x prime of t, right? Because it's a function of t equals kx. We can say x dot equals kx because it's a time derivative. So dots are for time derivatives. Yeah, we could also like write d dt and put the x out here, but that's the same thing. But in general, when you see a differential equation, convert it to this form. Why? Well, because when we solve it, this is how we're going to solve it. We're going to move all the x terms to one side and all the t terms to another. What do you mean by x terms and t terms? Well, we're going to do something that mathematicians don't like us doing, but we're physicists. We're going to break this apart into a fraction. So this becomes dx on the left equals kx dt. And now we want to move the x terms to the left. So we're going to divide by x and we'll get dx, or I'm going to put 1 over x in front. 1 over x dx equals k dt. Thunder outside. Okay. Now, why would we do this? Well, it looks an awful lot like we can just put an integral sign on both sides and solve. And that is what we're going to do. Now, if you really want to, you can prove that this works. But I'm not a mathematician, and this is not a math class, so we're not doing that. So integral of 1 over x is natural log. You will learn that it's natural log absolute value. And the reason is just because I'm not going to go into the reason right now. If you want to go into the reason, ask in hashtag questions in the Discord server or go on Khan Academy is my honest answer. It'll take you 5 minutes if you find the video. Anyway, so I just integrated both sides. This is a simple application of both these rules. So k is a constant. Um, I'll explain this. Um, uh, Actually, my room is kind of dark. Let me turn on my light. Okay. So, we have a constant plus c on the right side here. You might be asking why I didn't add a c to both sides. Remember, indefinite integrals, we add c. Um, just because, the constant, like I said, doesn't matter. I could add c to both sides, but this c on the left can be any value, and the c on the right can be any value. So we know if we subtract them, they can be any value as well. So we're just gonna put c on one of the sides. Does that make sense? Sorry. Anyone want me to explain that more? Okay, sounds good. And like I said before, that the C doesn't matter, quote unquote. It actually does because let's say that when I start out, you know, x can equal 0. Okay, let's say like when I'm like 5 meters away from my house, right? That um that's like 1 second away. Like after 1 second, I'm 5 meters away from my house, right? If this k value is like 2, that's not true unless I choose the right value of c here. So for differential equations, this just says how my x value is changing over time. It doesn't say how my x value starts off, right? Because if I have a differential equation saying like I'm speeding up in my car at 5 miles per hour, well, I could have started from like completely stopped, right? Or I could have already been going 100 miles per hour before I started speeding up. The differential equation doesn't tell me that. The differential equation only tells me how my speed is changing. And so what we need is what's called an initial condition. And in general, the theory of differential equations just tells us that the number, like the order of the derivatives. So if we have a second derivative, for example, we need two initial conditions. If we have a first derivative, we need one initial condition. So, and so on. So just to solve this out, we're going to put e to the power of both sides. E to the power of ln x is just x, right? And then e to the power of this is, I'm going to separate out the plus. So we're going to say e to the c times e to the kt. And since c can be any number, e to the c can be any positive number. So I'm just going to call that a, e to the kt. So boom, we solved our differential equation. Bro, okay. Any questions? How I did that? All right, let me go on the screen. Yeah, it would be helpful if you can talk out loud because I can't show the screen and answer questions, but I can zoom out. Sorry. Okay, looks like there's no questions. So that's how we solve a differential equation. We choose this a value based on our initial condition. So let's say that when I start out, I'm 1 meter from my house, and at time is 0, right? That just means that a is 1 because e to the power of 0. I'm gonna put this here. E to the power of 0 is 1, so a just equals 1. But if I wanted to resolve the equation with starting from my house at 2 meters away, well then all I'd have to do is set a equal to 2. Or if I only know how far I am from my house after 100 seconds, I can still plug that in and based on the value of k, solve for a. And so why do we care? Well, notably f equals ma is a second order differential equation. Why? Because a is x double dot or x double prime or d squared x dt squared, whatever you want to use. Either way, this is a differential equation with two derivatives of x. So let's just say that I have some weird expression like um, that, right? Let's just say I have some weird expression like that for f, right? Well, now I can solve for what my x value is as a function of time. So based on our physical laws, we can figure out how things actually move. Okay. Yeah, I think we're going to be done with all the harder calculus stuff soon. So, if you have any questions about differential equations or literally about differentiation, integration, anything, just ask now. Okay, great. So, I'm doing differentials and Taylor series together. Um, Again, calc class, you're going to learn about Taylor series. So, let's say we have this function, right? We might say like, well, what's a good approximation for this function? Well, at x equals 0, we know that it equals 1, but obviously the function, if you go any farther from 1, the function and this line aren't really close together, right? So let's change that. Let's add a term so that the lines approximately match together, right? So really close by, if you zoom in, well, these values are really, really close. So if you wanted to find e to the power of 0.001, well, the answer is really, really close to 1.001. Why? Just because we're matching the derivatives. We're making sure that the functions, they have the same rate of growth around the same point. Now, that's like not really that close though. How can we make it closer? Well, if we can add an x term to make the first derivative match, why not make the second derivatives match, right? So I got rid of this. Okay. Let's make the second derivatives match. I know that the second derivative of e to the x is 1. Why? Because e to the x, the derivative is e to the x, and the derivative of that is e to the x, and the derivative of that is e to the x. So at 0, they're all equal to 1. So, wow, that's a really good fit, right? If you zoom out, that's your quadratic, that's your e to the x function, and they look pretty close, right? Well, I'm sure we can do better, right? That looks even closer, right? Boom, and we get closer. And what Taylor's theorem basically says is if we there's no better way to write this in Desmos, but let's say we add up like 100 of these. It'll take a while to graph, but it'll graph. Um, Boom. They look like exactly similar. That's the e to the x function, and that's the sum. So what we're doing is we're just matching the derivatives. And you don't really need to know the exact details. This formula basically tells you how to match the derivatives. There's a reason there's a the reason there's a factorial. And so if you don't know what a factorial is, like 3 factorial, for example, just means 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. Well, if you take a first derivative, this 2 will come down and cancel out with this 2 factorial. Or if you take a second derivative, sorry, the 2 will come down and then a 1 will come down from the power rule. If you take the nth derivative, the n will come down, then an n minus 1, then an n minus 2, and all of these will cancel out with the factorial, and the derivative will be matched. So what's more important is that you can just use these to do something useful. So how do we do something useful with, you know, a Taylor series? Well, like I showed you, a mathematician might be like, oh, this sum is equal to the function. What I really care about is, well, if x is really close to 1, these two are basically good. They're both basically the same, right? And you might be like, well, why would we ever have a situation like that? Well, one example is, let's say that you're looking at the Earth's mass versus the sun's mass. Well, obviously the Earth's mass is really, really, really tiny compared to the sun's mass. So in that case, you might use an approximation. So you might, if your x value, for your x value to be really small, would actually be like the Earth's mass divided by the sun's mass. And these two functions would basically be the same. Why? Because m over m, it's like 10 to the negative, like, I actually don't know what it is, 10 to the negative 9, something like that. Really, really, really small. And so these two functions are basically the same. So, you know, why use the complicated expression when you can use the easy expression? And as you'll see in the handout, this is very useful for a lot of things. So we're going to do some exercises here. So I have this circle, right? And I'm going to introduce what's called a differential. So I'm going to take a little slice of the circle. How little, you say? Well, remember in our derivatives how we had like in integrals we had a piece dx? This is what mathematicians don't like doing, but we're going to do it anyway. The reason that we have this dx, like the reason that that's our notation for a derivative, is because the d just means a really, really, really tiny change in x. How small? Well, you're taking a limit, so the answer is actually 0. The change in x is 0. But it's you can also think of it as extremely, really, really tiny, really small. So I have a question. If we have this circle and I take this angle d theta, how big is d theta? Like I said, really, really, really small. Basically infinitely close to 0. So, you know, what does that mean? Like, is it not 0? I don't know. We don't really concern ourselves with things like that in physics. That's the best answer I can give you there. It's just a tool at the end of the day. And if it works, it works. And I'll show you here it does work. And I can't draw a circle. You're going to assume that's a circle. So I have a question. If I draw a flat line here, so this is, I'm just gonna, okay. Okay, cool. Sorry, does everyone understand the concept of differentials? It's like not that easy to wrap your head around. And if you ask your math teacher about it, they'll be like, no, that's a bad way of doing math. But it's very, very useful and very, very helpful for physicists in particular. So we're going to do things that way. And any good physicist will tell you that that's a good thing, differentials. So I have a question. If I take this circle of radius r and I have this piece d theta, I want you to DM your answer to me. How long is this length? This flat length here? Remember, d theta is really, really small. So I'll give everyone like 2 minutes. If you think immediately that it's going to take you longer than 2 minutes, you're overthinking it. I'd recommend spending a minute thinking and then giving an answer. So DM an answer to me, and I'll let you know if it's right or not. Try not to use any trig. Remember, d theta is really, really small. Yeah, I can't look at responses while having this up, so um hopefully you'll understand the question. I'll give you all a hint. So if you're trying to solve exactly for this length, you're thinking too hard about it. Like I said, d theta is so small that it's infinitely small. Basically, it's extremely tinily small. It's the limit of how small you can get. And so in that limit, is this instead of solving exactly for this length, what's a really similar length that basically has the exact same length that's easier to solve for? Notably not zero. Like you should have a d theta in your answer. Um, yeah, please DM me. Whoever just texted everyone. Okay. Anyway, I'm just gonna give the answer now. So, a common responses I got was um r sine of d theta, which is um correct and actually something I wanted to go over. And the way you get that is by splitting this in half. This is r sine of actually wait. How did y'all do this with okay. Yeah, I'll go over it. So, how did y'all get r sine d theta? R. The way I would do it is I'd split this in half and I would get 2r sine d theta over 2. Um, because we're taking this half piece of angle here, taking the sine of that and multiplying by r gets us this length here. And multiplying by 2 gets us this full length. Um, r sine of d theta, are y'all doing like, I don't know. Someone, holy hell. Sorry. Anyway. Yeah. Okay. Yeah, you just assume that this is basically right angle triangle. Sure, that works as well. But what I really wanted you to get was r d theta. I also got a lot of zero answers. R d theta is basically really close to zero, but you kind of also want an answer, right? Like you're assuming it's like as close as you can get to zero without being zero. So obviously, like giving zero is not a useful answer. So yeah, so what you could do is like assume that these, since this angle is so small, that these are both 90 degrees, and then you get r sine d theta, sorry. Um, but what I wanted you all to get was r d theta. Now, why is that? Well, let me erase this. The way that I, as a physicist, would think about this is, well, this length and that length are close enough. And why do I say they're close enough? Because, okay, if you look here, can you really even tell that this is not part of the circle just with your eye? Like if we zoom in, even if we zoom in, like you can't really tell that these are different. And so what I'm saying here is if d theta is really, really small, the length of this line and the length of this arc around are basically the same. And now I'm going to explain what basically the same means in more like formal mathematical language. But if I'm looking at this as a physicist, I'm thinking, yeah, this, it's close enough. And since r d theta is so small, this is just going to be r d theta. So now, okay, now what we're going to do is we're going to come over here, look at the common physics approximations. And would you look at that? Sine of x is approximately equal to x. And that's just because if we do Taylor series, you'll get that result. You'll get that sine of x is like x. You're red again, black. You'll get that sine of x is approximately x minus x cubed over 6, and so on. Plus x to the fifth over 5 factorial, and so on. It's like 120, right? And then minus dot, 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 right? So if we assume since d theta is really small, we can use our approximation, right? Because we showed that from the graph, like I got rid of it. Well, right here, they look really, really similar. For small values, they look really, really similar. And what we're saying with our differentials, right? To make our differentials formal, right? So we're explaining what a differential actually is. It's basically saying that it's small enough that all functions are the same as the very first term of their Taylor series. So if we use sine of x is approximately to x, this gives us this equal to r d theta. And using the same thing over here, again, r d theta over 2 times the 2 is be r d theta. And so what this basically says is we're ignoring all these terms because d theta is so small that if you take the limit as d theta goes to 0, this x cubed goes to 0, this x to the 5 goes to 0. Yeah, so like for example, if you have like theta equals 0.01, that's like 0.01 minus 0.01 cubed, that's like 0.00000 and one more 0.1 all over 6. Like this term basically doesn't matter compared to this term. And adding the x to the 5 term, that doesn't even matter either. And so when we do approximations in physics, what we're basically saying is we're using these Taylor series approximations to say that the function is approximately equal to the amount that it changes by in the first step. This is probably like the hardest thing that we're gonna do today. It's very, very different to something you might have seen in math class, the way you've thought about in other classes. Um, but approximations are very, very important in physics. So there's like I said, I'm just gonna go over again a couple ways you can think about this. One is like the geometry approach, the physicist mindset, which is d theta is small, so these two are probably not probably, but like you know that with experience they're really, really close to each other. The other way is, well, me as a physicist, I think, or not sorry, not me as a physicist, but looking at it mathematically, if you take this length and subtract this length, so I'm gonna recolor code these. So if I take this length in red and this length in black, or let me get a different color. This length in purple, right? This length over here is RD theta. Notably, I'm using radians, so that's why we're just multiplying by d theta. And if we subtract out this, let's write it out as r sine theta, r sine d theta. Well, using our Taylor series from here, this is basically approximately equal to uh, d theta, well, r in front, but d theta cubed over 6 plus d theta to the 5, and so on. And now I can like fully explain what a differential means. A differential means anything that isn't first order in the differential. So order is the word that we use to describe the power of each term. So first order is the term that has x to the power of 1. Second order is term that has x to the power of 2. Third is x to the power of 3, and so on. So a differential is just something that we take d theta matters, right? So d theta to the power of 1, first order matters, but d theta to the power of 2, we say that's equal to 0. Or d theta to the power of 3, we say that's 0, and so on for all of this. And so differentials are just a way in physics for us to find, yeah, so since d theta is so small, d theta squared is like incredibly infinitesimally small. And so when we compare the two of them, like this is, we just set this to 0 because d theta is so small that we only care about first order in d theta, but we don't care about any higher order in d theta. Okay. Yeah, if anyone has any questions, like please ask. Like this is important and also not really easy to understand. I'll just say like again, so you can look at it geometrically. You can look at like the difference between these two is greater than first order, so they're basically the same, right? You can also look at it in a Taylor series way. You can find this exactly and then take the Taylor series. All of those are equivalent. So when we're using differentials, it's just however you want to get to the fact that second order and onwards doesn't matter. And personally, like when I'm actually doing physics, I would just by experience know that like these are the same to first order, and therefore this length is just RD theta. And sometimes if I'm dealing with something complicated, I might take a derivative, find a Taylor series, and then take it to first order, and so on. Anyway, any questions? Yeah, sure. So, sorry, the flash flood warning. Okay. So differentials are just ways that we can, so if I put a D in front of a letter, it's like a very, very small change or a very, very small amount of that letter, right? So like if I say like dm, that's just a very, very small amount of mass, for example. And what that means like mathematically is it's so small that I care about like this to the power of 1, but if I square it, it's so small in comparison to this that I don't care about it. Dx is like a little tiny piece of length. So that's what we were finding here, dx, a little piece of length. and d theta is like a little piece of angle, so that I care about d theta to the power of 1. It's really, really small, but it's small enough that I don't care about it. I still care about it to the power of 1, right? I'm not going to say it's 0. But if I square it, it's so small that squaring it makes it like basically 0 in comparison to d theta. So it's just a mathematical tool. And it's the same reason why we have a derivative is like df dx. We can just say that df is a tiny, incredibly small change in f, and dx is a tiny, incredibly small change in, sorry, df is a tiny, incredibly small change in f, and this is a tiny, incredibly small change in x, and we're just finding how they relate to each other. And so we can treat these little bits as parts on their own and use them in our physics problem solving. And so what I just went over basically was the rules for differentials. You can either solve for length exactly and just use a Taylor series to get the power 1, because like I said, power 2 and onwards is 0. Or you can use geometry and like just approximate the two as similar. And that requires just experience, really. Does that answer your question? Okay. Again, like if you really just want me to explain everything again, or if there's any one part you want me to explain again, like don't hesitate to ask. Okay. Yeah. If you still want to ask, like even after I move on, like don't hesitate. Anyway, so let's just do some like examples, right? Let's say that I'm doing a problem where I'm throwing little bits of mass at a planet, right? Like I'm throwing balls at a planet, okay? So I might say that each ball has a mass dm and the planet has a mass capital M. So I get this as my answer, okay? For like, or let's say like V naught, okay? Or I'll go over this later. Let's say this is my answer, okay? And well, I want to get a simplified approximated version of my answer. Since this dm is so tiny, I can just use this common physics approximation, 1 plus x to the power of n. Well, the power of n here is 1/2. Does everyone understand that? Because raising to the power of 1/2 is the same as taking a square root. Okay, that sounds good. So looking at this common physics approximation, 1 plus something on the inside to the power of n is 1/2 here, is approximately 1 plus this something on the inside here, divided by 2, since we're multiplying by 1/2. So this is approximately 1 plus 1/2 dm over m. Now, why can I do this? It's because dm over m, I know that dm is our differential, right? So it's incredibly small. So this entire thing is really, really small. And since it's small, I'm allowed to use this approximation here. And this Taylor series is going to have more terms, right? Like the next term in the Taylor series is, for a square root, is dm over m squared here. But remember, we don't care about differential squared, so we're going to get rid of that and everything else that comes after. And that's our differential approximation. So that's how we're going to use differentials. So let's just say like I somehow set this equal to some change in position x, right? That's just what I get out of after I do all the math in my problem. Now I can rearrange this and get a differential equation. And if you're unsure about how, you just have to solve for dx divided by dm, and you'll get a differential equation because that's a derivative, right? Um, you can you can use this in any physics class, but this is most likely not going to show up in like AP Physics. This is like one of the most advanced things we were going to cover today. Like, one of the common things that shows up in every physics class is like a pendulum, right? So if you're solving the problem for a pendulum, and this is on the problem set, so a pendulum displaced by some angle theta at the start, right? And it's gonna go backwards and forwards. And you'll learn a formula in AP Physics 1, but your teacher will never explain where the formula comes from. Well, the reason the formula comes from where it comes from is we assume that this initial angle is so small that sine theta, sorry, my mouse isn't working. What is this? Okay, sine of theta is approximately equal to theta. And that's how you can use this. And so you're not going to always have a problem where you can approximate, right? Like if you have two masses in a problem and there's like 5 kilograms and 7 kilograms, like you're not going to use this, right? But I'll say the places where this is useful are when you're dealing with small changes, right? Which again, your mind might immediately go to derivative, right? But sometimes it's kind of hard to figure out a derivative in a physics problem unless you say, well, let me change a little bit by x, and then I'm gonna use this little variable called dx, calculate how everything changes, approximate, and then I'll see how this other thing changes. And then you can get a differential equation. Or like in a certain geometry things, right? Like the circle thing I showed, it's very common to have a setup like this where it's easy to approximate this length as RD theta. Or again, you might have like a situation like this where dm is much smaller than m, and then again you get approximation. Okay, we don't have much time. I'm gonna keep going. Hopefully finish like 5 minutes late, but you can obviously leave if you have somewhere to go. So, error propagation is going to be um on the F equals MA. So we're just gonna go over it really quickly here. So error propagation just means yeah, I'm just gonna go over the example. So 3 students make measurements of the length of 1.5 meter rod. I'm just gonna do Alice's error, and we're gonna not let's do the rest of it. So there's a few error rules that will be on the handout. Um, so if you have the error in uh one thing x and sorry, if you have two variables x and y, the error in x plus y. So error we just denote with this delta symbol here. Okay. So what does error mean, first of all, in an experiment? Well, if you're going to do an experiment and you're going to get data, you're not going to know exactly what your numbers are, right? You're going to be like, well, I think it's 5 millimeters, but my ruler only has spacings every 1 millimeter. So it could be like 4.5 millimeters. It could be like 5.5, but like it's just closest to the 5 line. So we're going to call it 5, right? And so your rules are this. This is actually like the one important rule. You can derive there's like a more general rule as well, but you can also derive what's called the product rule from this. And so let's say you have one measurement of length and another measurement of length. To get the total error, you have to do what's called adding in quadrature. You add both things together and you square it. And the reason we do that is based on it's based in statistics. If you want to see the derivation, I can link uh the handouts by someone named Kevin Joe. He will the derivation is in there, but it's like very much beyond the scope of this course. But you're gonna have to use this formula, these two formulas. And so everything that you need mostly is in these two formulas. There's also um one more, but we will cover it in the handouts. Okay, and so I'm just gonna do this problem here. So she makes a single measurement. Okay, well, there's no calculation there. Okay, so he takes two measurements using a wooden meter stick, each to within 2 millimeters, and then he adds together. So he takes measurements of a 1.5 meter rod, right? And then, okay, actually, apparently it might not be in the handouts. It is kind of, um, yeah, okay. So let's just do Bob's, right? So he takes two measurements. Um, Actually, I'm not sure how this is phrased, but so each to 2 millimeters. So our relative error is plus or minus 2 millimeters here. And he's adding two measurements together of this 1.5 meter rod. So we just use this formula and we just have to to find the error of the total sum. You just have to find the error squared of one and the error squared of another, take the square root. And that'll just give you 2√2. Okay. So yeah, this is basically what's happening here. Um, Sorry, we're running out of time, so I'm trying to get to units and dimensions. So uh, okay, so units, we have to have a method to measure stuff, right? So we use seconds for time, meters for length. This is really not that difficult if you're used to it. There's 7 base units in the SI system, but we're doing classical mechanics, right? So we're really only ever going to see meters, seconds, and kilograms. So for example, you might see like force is in kilogram meters per second squared, time is in seconds, speed, meters per second, stuff like that. But we also have something called dimensions. So every quantity in physics has dimensions, and it doesn't matter what unit system you use, it still has dimensions. So for example, speed is a length divided by a time. You can't have a speed without going a certain length at a certain time. So I don't care if you're using miles per hour, kilometers per second, meters per second, light years per second, you're still going to have dimensions. And so what we can do in physics is called dimensional analysis. So let's say that we know, or let me just do the example. So we know that the spring has a certain force and we want to find a frequency. So let's write down all the, let's write down all the relevant variables. So we know M is a mass. So that has units of M. We're going to write it like that. So that's for mass. Okay. Then we have K. And I'm not going to go over how we get this, but this K will have units of mass divided by time squared. And the way we get that is we have to know the units of force and then divide by the units of distance to get this K units. So, and then we have the units of frequency, which I'm going to use omega for, and that's 1 over time. So the way units work is whenever you do anything with two quantities, right? If you multiply two quantities, let's say A equals mk. Well, now A has dimensions. A has dimensions of mass squared per time squared because we have to multiply the dimensions of these two together. So the reason I got Fk is I did F equals Kx, right? I know that X has dimensions of length, and I know that I know that F has dimensions of mass times length divided by time squared. This should be on the outside. And so just by dividing this, I get this here. And so I'm just going to give you guys the answers because we don't have time for me to do this. Omega is square root k over m. So how did I know this? I know. Sour, leave me alone. Okay. Well, we take this k, dividing by m, sorry, gives us 1 over t squared, and taking the square root gives us 1 over t. And so we can also add some constant c here, and this constant is unitless. So For example, omega could be 2 square root k over m. And the reason we know this is true is because for omega has to have 1 over time units. It's a frequency. A frequency is just like how many times something happens per second, right? So per second would be per time unit. And so just from units, we were able to figure out that this omega has to be proportional to, so that's what the C is for, has to be some multiple of square root k over m. Now, if you have a complicated dimensional analysis question, what you should do is just write out the units of everything that you want, right? So let's say you want to solve for omega. You should write m to the power of a, k to the power of b, where a and b are just numbers, rational, like they're numbers, okay? And so what you do is then you plug in the units for m and the units for k. And then you also plug in the units for omega on the other side. And then you match, you have to figure out, you have to make sure that the m units on both sides of the equation match, and the t units on both sides match. And also the L units, we don't have any L units in this question, but if we have L units on either side, they also have to match. So you basically can solve for A and B to get the correct units. To get the correct values of A and B based on the units matching. Does that make sense, everyone? I can do the calculation, but we will be going even farther over. Okay, and then that's how you do dimensional analysis. So this will again be in the handout. And then limiting cases is basically saying, like we did for the derivative problem, you think about how the function looks when it's really small and really big. So for example, we have this question. So we're throwing a ball up and it's landing on this corner. So we have to figure out which of these is correct for our expression for how fast v0 has to be to get up on this corner. So what we can do is say we could solve it, but we could also say, well, if theta is like, or let's say if L is 0, right? Well, then we don't need any speed to get up there. And well, that seems to work for everything, right? We don't need any speed if L is 0. Great. Now, let's look at what happens for different values of theta, since obviously that seems to be the key factor here. So if theta is 0, then no speed will work to be able to get it all the way up here, right? Or you need to go, the closer you get to 0 for theta, the faster. Oh yeah, notably you're right. Okay, yeah. Um, sorry, yeah. If you throw it down here, it's not going to get up there at all. But let's say you throw it exactly at 45 degrees. Um, then if you throw it exactly at 45 degrees, well, no matter what you do, gravity's going to pull it down just a little bit. So you have to throw the faster and faster you throw the ball, the closer and closer it'll get to hitting this mark. You have to really throw the ball infinitely fast to get it to hit this mark, to get it to hit this corner when there's gravity at an angle of pi over 4, 45 degrees. So we can plug in pi over 4 here and see which of these work. So we know that tangent pi over 4 is 1. And so these two in this case work because we get a v value that's getting closer and closer to infinity as we plug in theta equals pi over 4. And then we can just check these two cases for theta getting closer and closer to 90 or pi over 2. Yeah. And again, notably, we need it to tangent of pi over 2 um, goes to infinity. Um, unless we, of course, have a cosine. So yeah, we sorry for going over time, everyone, but yeah, so you just consider the different values of theta until you can figure out what you expect the answer to be. Okay, anyone have any questions about anything that we've gone over today? Okay. Yeah, we will post handouts tomorrow, so they will have questions on them. And yeah, just you can ask any questions you have in this or in the server. And yeah, it's gonna cover everything that we've gone over already, just in more detail. Yeah, if anyone has any questions, you can stay, but otherwise we're done for today. Okay, bye everyone.
Bye. Thank you.